Hi, I'm Nicole. I'm Emily, and we are the horizontal filtration subteam. So the horizontal filtration subteam, its goal is to build the horizontal filtration system, which is an attempt to make a better sand filter. So our team's goal is to develop a compact and sand filter that is easier to assemble and easier to transport than the current STARS model. So its primary goal is that it'll have less volume, have the capability of origamiability, so that you can easily take it apart and build it back again. And then it'll also just overall be a simpler and easier filter to use.
So the basic idea of our filter is, you can see that it's basically two vertical plates with slots in them and sand in between them. So right here, the water flows down and it's angled. This angled shelf guides the water into the filter. And then there are angled slits right here that let the water in to the sand filter portion, but are angled so they keep the sand in. And then so the water flows down here, flows horizontally through the sand filter, and then flows up and out the other side. So as you can see, here is the water. Here are the angled slits. So they're angled as steeply as we can fabricate them to keep the sand in while enabling the water to flow in. And then it passes through the bed of sand where contaminants and particles get trapped, and then it flows out through the other filter slits on this side and up. And so that is the forward filtration component. That's when the plant is running. But then eventually the sand filter gets clogged and it gets saturated with particles and contaminants, and it can't filter effectively. So then we have what's called the backwash stage, which is how the filter gets cleaned. So you see these angled plates on the sides. During forward filtration, they guide the water into the filter. But then during backwash, there is a siphon at the top of the filter that opens, and it sucks water up and acts as a vacuum. So then it basically forces the plates, sucks them against the sides of the filter, so it stops water from flowing in the slits. And then there's one slit at the bottom of the plate that enables water to come in, but then it's sucked out the top at a high velocity. So this, it's at a high enough velocity that it causes the whole sand bed to fluidize, which essentially, since the contaminant particles are lighter than the sand, it'll cause the contaminants to float to the top and get sucked out while the sand stays in the filter. And then once the filter is clean, the siphon is closed and forward filtration resumes.
So to test this design, we wanted to run some experiments, and we thought that the filter shells would be the most uncertain part of the whole design. So based on last semester's experiment, which consisted of a pipe apparatus that kind of simulates the filter shell design. So basically, it's the inlet with the sand and water flowing through, and then the outlet, which is basically modeling the filter shelf. So we decided to use a similar design and then test it again to make sure that the filter shelf actually works as it's intended to, and that the sand will actually stay inside the filter and not travel too far up the shelves.
So our goals for this semester were, so last semester they performed similar experiments to sort of verify that this would be practical, and they determined that the level that the sand rose depended on the velocity of the water. So we wanted to test that theory out with conditions more similar to a real sand filter. So we first did it with, as in the previous slide, we first tested with a vertical pipe and then an angled pipe. And then something we want to do in the future is test with conditions more similar to an actual filter, which is having a flat plate instead of just a round pipe, because we want to make sure that the different geometry doesn't affect the water flow too much. So our initial plan was to construct something that looked a lot more like the actual filter, which is a box with angled plates and sand between them. But we decided that that would be hard to construct for just an experiment, because you'd have to make sure that the box is watertight, and it would be unnecessarily difficult. So our plan now is to create a pipe and then put a flat plate inside the angled pipe. So just modify our current experiment.
So when we first ran the experiment with just the pipes and no flat shelf, we encountered several problems. So for the apparatus, we had to PVC weld the outlet to the outlet to the inlet, and because of that, there was a potential possibility of it not being watertight enough. So when we first ran this experiment, we noticed that, so we had to fix that by PVC welding more. And then we also noticed that the fittings on top of the inlet and outlets were did not fit as well as we thought they would, which caused some water to leak out. But primarily our issue was that when we first ran the experiment, the entire bed of sand lifted up, and we realized that this was due to air bubbles trapped in the sand, and you can see this in the video here. Yeah, you can see that the sand is being lifted up from the by the air bubbles. But we did realize that if you lightly tapped on the apparatus and loosened up the sand a little, that would resolve the issue and loosen up the sand and get rid of the air bubbles, so that this would then allow the sand to fully fluidize, as you can see in this video. So here, with all the air bubbles out, the sand was able to fluidize as we originally intended it. However, there was still a problem where after we got rid of the air bubbles, we tried to run the experiment again, and the problem returned where we still saw air bubbles. So each time we ran the experiment, we kept having air bubbles and kept having to remove them.
So what we found was for the first time and subsequent times we ran the experiment, our findings were more or less the same as last year, in that the sand, as you can see here, it started at a level, after we poured it into the pipe, it hit a level about 3 centimeters from the bottom of the pipe, the angled pipe, but then when it was fluidized, it rose about 4 or 5 centimeters depending on the trial, and then it stayed there as water kept flowing. So there was an initial rise, and then it was still. And if that is the case, then this shelf design is feasible, because we can design shelves that are longer than the rise in sand to keep the sand from leaking out. And then based on their findings last year, we would expect this to vary based on the water velocity. And we did all of our trials with a pipe that went up to 100 RPM. And so we did our experiment at 100 RPM, but ideally in the future we want to find a pump that can make the water flow faster and measure that. But then we did notice one interesting and possibly troubling thing, which was we ran the experiment 3 times, and in between iterations we didn't replace the sand in the filter. So what we did was we ran the experiment, and then we stopped the water and let the water drain out of the pipe, and then ran it again later. And what we found is that the sand rose each time. The sand, while the experiment was running, the sand rose. It stayed at a steady level, and then it sank back down a little bit once we drained the water out, but it didn't sink back down fully. So each time we ran the experiment, more sand flowed into the angled pipe. So this has implications for, say, if the water flow in the filter wasn't constant, if the plant was run and then shut off and then run again, or if the flow rate wasn't constant, even if we could design for the initial sand rise, we wouldn't be able to predict how high the sand would rise after a long period of time. But we just need to make sure that this wasn't caused by an issue with our experimental setup and that it's an actual relevant effect.
So some future tasks that the future subteam for horizontal filtration could focus on is to finish up the filter shells test, primarily at a faster output velocity because, like as Emily said, we were only able to find a pump that its max velocity was at 100 RPM, and at faster velocities, the filter shelf could have a very different result. So we would want to test it at faster velocities and find the max possible velocity that would allow the filter shelf to still function as it is designed for. And we would also want to test for the multiple runs effect, which Emily was also talking about previously. And then if the possibility that the filter shelves aren't feasible is true, they would have to find alternatives such as potentially a mesh filter. And after the filter shells issue is resolved, we would want to test the backwash stage, which is also a part of the design that may potentially have issues. And primarily for this experiment, we want to test if the particles will actually fully separate from the bed once the sand bed is fluidized. And then, of course, when all these issues will be resolved, we will want to fabricate the actual horizontal filtration design and then test it once again to make sure that it will work as we would like it to.
Thank you for watching.